Anything you want to clarify before we start
No.
doing the worksheet?
Okay.
Okay, these are the formulas. This is definition. This is a capacitor in parallel, capacitor in series. This one you don't need to memorize all. Memorize this one. This one is half QV. Right? This is like kinetic energy, half mv squared. Then you can derive using this formula if you need to use this formula. Okay, let's try some question. Okay, let's try exercise number 1. Exercise 19. An uncharged capacitor 0.10 microfarad capacitor is charged to a PD of 500 volt by a battery. Calculate the energy stored in the capacitor. Yep. Right. Half CV square. Put in the value. Right. Convert to SI unit. 500 volt. Get your 1.25 times 10 to the power minus 2 joule. Right. Just circulate in the battery. Half. Right. Convert to SI unit. 500 volt. Can get the answer? These are elementary calculation. You should be able to do that.
Yep.
Right. Supply of battery is QV. Heat dissipated. Energy supply minus energy stored. Okay, energy stored. Energy supply. It's energy supply. So these are two different. Energy stored and energy supply is different. Okay, can get okay. Given a number of capacitors, each with capacitance 2.0 microfarad and a maximum say working potential difference of 10 volt, how would you construct capacitor of 1 microfarad suitable for use for 20 volt? Yep. Yep, this one you must know your resistance in series and parallel formula by a fingertip. For series, you take the reciprocal of to find the resultant capacitance. Yep.
Okay.
Like that, oh. Do in series. So you take reciprocal, you get 1 microfarad. Oh. How about 2 microfarad? Capacitance suitable for 20 volt. You cannot use one. One will, your capacitor will break down. So you have to use more than one. Yep. Two in series, connect the two in parallel. Okay, now. Right, these two combined.
Okay.
These two combined will be one. 1 and 1 in parallel. You add them up. 2. Okay. In the circuit below, the cell has negligible internal resistance and EMF of 50 volt. The switch is turned to A. This one is charged up. What is the initial charge? Initial charge on the 2 microfarad capacitor. 50 volt, 2 microfarad. Use the formula calculator. Yep. Can get answer.
Yes.
The initial potential different across the capacitor. What's the PD across this capacitor? As you close the switch, it's instantly charged to 50 volt. A lot of current will flowing to 50 volt. Calculate the energy stored. Yeah. Getting you to use a formula, that's all. The energy stored in the capacitor is half QV, half Q, that's your Q. V is 50 volt. Can get the answer?
Yes.
Okay, good.
The
Okay,
generator is half QE square.
no, half QV only.
Oh, okay, okay, okay.
Supply is QV. Supply is QV. So it's half QV. Okay, no?
Hmm.
If you've forgotten your formula, just refer to the refer to here. Half QV. Okay, the next one is similar to YouTube, where this is low pressure, this is high pressure, so it will rise up until the pressure is balanced. So if you make the two high pressure, then this one will go down until both of them are the same level. Okay. Okay, if you can see, okay, if not, it's all right. Okay, just to draw analogy between them. Okay, now your switch is moved to B. What is the final potential difference across each capacitor? Yep,
Finals.
2 microfarad. Initially is 50 volt. So this one is 0. So the charge will flow until both of them have the same potential difference. Right? Then the final potential difference be V. Conservation of charge. The initial charge here is distributed between these two plates. That's the final charge. So total initial charge equals total final charge. Initial charge, right? We have calculated earlier. Initial charge, store here. Final charge, right? Final charge would be 2 plus 3 times V, right? CV, CV, we are using Q equals CV. C is that one there, and that one there. Change to SI unit. Calculate 20 volt. Can get.
Yeah.
What is the energy stored in both capacitors? Energy stored is half CV squared. Right? Use the resultant capacitance, use the resultant voltage, the final voltage. Right? They are in parallel. So you add them up and 10 to the power minus 6, so 20 volt.
Oh, teacher.
Say again.
Teacher. Just so if it's energy stored, then it's half QE, but if it's oh yeah, yeah. QE square.
We use the
Okay, okay.
resultant capacitance of, that's the resultant capacitance of, and there's your 20 volt, final potential difference. Account for the difference in the two answer. Right? A lot of current is going to flow. So energy is dissipated in the wire. Yep, wire will heat up as a charge flow. Okay,
Hmm.
In charging a capacitor, half of the energy supplied is lost in the connecting wire. That's the reason. Okay, I think I will let you do that as a homework. I can try all the rest, your past year question as your homework. Let's go to, maybe we try number 6. This one, if the radius of a spherical conductor is R, what's the capacitance of the capacitor? First, let the charge of the capacitor be C, be Q, and the potential difference of a charge sphere. Yeah, is that? Then use definition to find capacitance. Right? Q over V is the definition. So we just cross multiply. Q, V take it down, 4 by epsilon naught, take it to the other side. Okay,
Oh, okay.
okay, let's go to discharge capacitance. Page 146. Okay, discharging a capacitor, 19.3. Which is charging when the switch is at A or B? Yeah, which is charging when the switch is at A or at B?
Charging, B.
Right? It should be at A, because there's a energy source, there's energy source.
Oh, yeah, yeah, yeah. Oh, yeah.
Right? In charging, we need a source of energy, a battery. Right? There's a battery if it's charging. So the current is flowing this way, flowing this way. What's the purpose of the resistance in the circuit? Right? Without the resistance, this one charge on very fast. Right? Resistance is to slow it down. When the switch
Oh,
is
to
at A,
control.
the capacitor charges up instantly, very fast, because the resistance wire is very low. When the switch is at B, the capacitor discharges, the resistor Q slows down. Right? That's why it's happening. When you put the switch at B, that's why it discharges. Right? Previously, the current is flowing clockwise, now it's flowing anti-clockwise to the resistor R. Assuming cell has zero internal resistance and EMF epsilon, the capacitor or capacitance C is charged to EMF. Right? It will charge to the EMF of the cell. So usually EMF of the cell, we call it V naught rather than epsilon. Right? V naught to show its initial voltage. And X can be Q, can be V, can be I. And that shows you when it discharges, it decays. Right? The same formula we use. R is the resistance of the charging circuit. That one. C is the capacitance. D is the time it takes to discharge. That's the alternative way of writing exponential. Decay start at V naught. Right? Start at V naught. Start at V naught. And the voltage decreases with time. This one becomes nearer and nearer and runs parallel and meet the time axis at infinity. Right? Don't worry about derivation. Just remember the graph. Right? Start with V naught and get closer and closer to the time axis there. And that's the formula for voltage. Negative sign as a current flow. Right? Sometimes don't have to worry about this negative sign because it's flowing this way. Previously, when it's charged, it's flowing that way. Right? Don't worry about negative sign. Discharging, right? Discharging, you have this one is charged up initially to V naught, capacitor charged up to V naught, then you close the switch, and there's your R. If the initial voltage across the capacitor is V naught, the voltage at time is given by that equation. Voltage across R decreases exponentially. Right? This is a symbol tau for time constant RC. This is the resistance of the resistor multiplied by capacitance of the capacitor, and it's known as the time constant, which has the unit of time, no? Right? Time constant, unit of time. How do we define time constant? Time constant is the time taken for the voltage to across a resistor to decrease to 1 over E of its initial value. 1 over E is about lah. Usually we are not particular about accuracy lah. We want to sketch the graph, that's all. Just about 37% lah. I can put RC inside here. Right? RC and tau will cancel off. RC and RC will cancel off. So it's minus E over 1. So E over 1, that's what we get here. E is 2.7 times 7.18. And that's the graph. This one show more clearly. It runs parallel. It didn't touch the axis, only at infinity. What is V? That's your 0.37, that one, 37%. And this is a time constant. Same if it is charge or current. Charge, that one will be Q, that's all. Right? Q equals CV naught. That's the definition. The definition formula, CV naught. Current is the same. I naught. Right? I naught is V naught over R. So if there's your charge, the graph is charged, Q naught, that will be Q. Okay, any comment? Anything you want to ask?
Okay.
More question, let's carry on. Right? More accurate. Right? The voltage decreases by 63%. Either 37 value is 37% or decreased by 63%, same thing. Right? By one time constant, that's one time constant. So by 5 time constant is 99.9% discharge already. So you can consider almost zero already. Discharge completely. How is time constant and half-life related to each other? Right? T is the half-life, is the time for the current to decrease to its half its original value. Okay, that's the formula for current. Right? If T is capital T, half-life, then I is I naught over 2. I naught and I naught cancel off, then you invert it, then you get your equation. Okay,
Hmm.
you will study more detailed half-life in nuclear physics. So we can see that half-life is greater than time constant. Any comment or anything you want to ask?
Nope.
Okay, as I say, we don't worry about derivation. Right? Initially, it is V naught or E. As the capacitor discharges, the PD across the capacitor decreases. The charge also decreases as the V decreases. As I said, don't worry about all this derivation. Just know that it starts with E, the initial voltage E, V decreases with time. Right? That's your graph. I'm just repeating. Discharge, charge on capacitors Q, right? As V decreases, Q also decreases. Q equals CV, V decreases, Q also decreases, C is the one that's constant. Okay, so you should be able to write initial charge is CV, CV, V in this case is E. Same formula, same formula, right? Except E replace it with Q naught, no? That's your Q naught. Okay,
Hmm.
okay, try this question. If the capacitor is initially uncharged and we want to charge the voltage Vs in the RC circuit, you won't be tested about this. This is extra knowledge. Initial current when the switch is closed, initial current, the resistor in the circuit slows down the charging of the capacitor. So initial current is just your Vs divided by R. That's 50 milliampere. Time constant you should know how to calculate. Right? RC, and sketch the graph. Right? Don't worry about this one. This is just, right? That's how the graph looks like. The charge will accumulate, the current will decrease to zero. Right? This extra knowledge for you for charging won't come out. Discharging, yes. Right? Charge up to 5 volt. The discharge current is opposite to the charging current. Right? You close the switch, battery here, you charge it up. Now you replace the battery with a wire, the current will go the other way. Right? Don't worry also lah. Charging and discharging current. The discharge current is in opposite direction to the charging with the initial current. Yeah, initial is just 5 divided by that. Media across capacitor decreases as it's discharged. See the following circuit. The capacitor is initially charged. Right? There's 5 volt across the capacitor, and the switch is initially open. At time 0, we close the switch. The voltage across the capacitor decrease discharging through the resistor. That voltage, the current will flow through that resistor R. And there's the formula. Right? Voltage across the capacitor will decrease. Anytime is given by V naught. V naught is initial voltage. In this case, it's 5 volt. Right? Time constant is 100 times 20. Okay.
Hmm.
Right? That's the discharging. This one put a negative sign, but you don't have to worry about negative sign because it's different direction from the original current. Right? But the graph is the same as the voltage, same shape. Right? 1.7 is 37%, and there's your time constant. Right? That's how you get your estimate your time constant. Right? It's 37% of 5 volt. Join it up. There's your time constant. It's about 2 milliseconds. Okay, try. A capacitor of capacitance C is charged to a PD of V0 and discharged to a resistor. The current flows at discharge is measured at different times. A graph of I against T is plotted. What does A, the y-intercept, represent, and B, the gradient, represent? Write down the equation. I0 is V0 divided by R. That's the initial current. And that's the decay formula for current. Taking natural log, ln I, ln I0 minus ln T over tau is RC. Compare with the equation of a straight line. The y-intercept is I0. Gradient is minus 1 over RC. Can? Okay, let's try. This is a formula that you need to remember. Right, for this formula, and then what is the time constant? This is the general formula for I, Q, or V. Two charge capacitor or capacitance, 2 microfarad and 6 microfarad respectively, and a 250 to 5 mega ohm resistors are connected as shown in the graph. What's the time constant? Yep, what's the time constant? Combine these two together as one capacitor. Combine these two together as one capacitor. Right? Combine this as a combined resistance. So 2 and 1, 2 microfarad and 5 microfarad. Find the resultant. Right? So it's 1.5. Resultant resistance, half of it is 2.5. The time constant is resultant capacitance times the resultant resistance. Okay, it's taken from STPM question. The initial potential difference across capacitor is V0 when the capacitor discharged through a high resistance. The potential difference decreases to 0.5 V0 in time t. The capacitor is then charged. The capacitor is then charged until its potential difference is 4 V0. Find the time taken for the potential to decrease to 4 V0, from 4 V0 to 2 V0 and V0. Right? Try it, give you a bit of time to try it out before I give you the answer. Just use the exponential formula. Right? Exponential formula, you should be able to code it. Then 0.5. Right? There's your T. Yeah, to discharge to high resistance capacitor. Got 10 more minutes. Right? Decrease to 0.5 V0 in time T. That's your 10. It's given that V0 cancel off. So it's 1.440. 445, take it down. Okay, should be able to write this equation down for V0. And then this is your time constant. Okay, time constant that we have calculated. And then 2 V0. Okay,
Mm.
same. Right? That's the exponential equation. V0 and V0 can cancel off. 30 is 2.0 tau. Can or not? Anything not clear?
Yeah, I'm still like learning.
It takes a while for you to accept the formula lah, but yours is very simple lah. No charging. Charging is more complicated. Discharging is more easier, one formula to memorize. Try this one. Capacitor is connected in series to a switch and a resistor. A voltmeter of high resistance is connected across the capacitor. The switch is closed. A set of value for V over a time period 20 seconds is obtained. A graph of ln V against T is plotted. The time constant of the circuit is, memorize this formula, either E or V naught. There's the initial voltage. Okay, this one can be E, can be V naught. Then taking ln, we want ln, taking ln, and compare equation of a straight line, gradient. Gradient in this case is 2, it's negative. 2 divided by 20 is minus 0.1. And we know it's 1 over RC. Can get?
Mm. Yeah.
Okay. A 4 microfarad capacitor which is charged to 24 volt is discharged to a 25 kilo ohm resistor. What fraction of charge remains in the capacitor 15 seconds after the start of discharge? Right, write down the equation. The time constant. Time constant is the resistance as a capacitance. Calculate out. Right? Know the formula to use. Exponential, we just take a Q naught down, that's all. Because you want to find the fraction. Right? Tau is 10 seconds. That time constant is 10 seconds. Minus, that's what we want. What's the fraction left? Can?
Mm.
Anything? Anything not clear?
I just need to be familiar with the formula.
Basically, memorize the formula and use it. Very straightforward. Okay, have a go at this one. You won't come out charging, but it should be similar to discharging. What's the capacitance of a capacitor? How to solve this equation? Right? Time constant, RC. So at one time constant, R is I naught over E. Two time constant, 2RC. Right? So the first time constant is I naught over E. Second time constant is divided by E again, no? I naught is your I naught divided by E. So 2RC is 10. Can STPM is more challenging now, more hard lah. You want to
Oh, is this
try that?
STPM questions?
Can or not? Can or not? Can or not?
Yeah. My teacher, is this STPM questions?
STPM is tougher lah because you have to go charging and discharging lah.
Oh, this is STPM.
This is from STPM because when it came out, there's
Oh,
no source to get the question. So I have to use STPM. Okay, we have completed. Any question here you want to ask? You still got about 2 minutes. Maybe we can solve some question. You can try some partial question. Under the worksheet, page 150. Capacitor consists of two metal plates separated by an insulator, as shown in figure 3.1. The potential difference between the plate is V. The variation in V or magnitude of the charge Q on the plate is shown in figure. Okay. Yep, that's the graph that's given. Explain why capacitor stores energy but not charge. Yep, can remember?
stores energy. I don't know the reason.
Explain. When the two plates are close together, one positive plate, one negative plate, equal charges on either plate. Right? The energy is zero. But when you pull it apart, work has to be done. So the work done is stored as electric potential energy. That's all you need to explain. Charges on plates are equal and opposite, so no resultant charge. Energy is stored because there's a charge separation. You pull it apart, so that's work done. Use 3.2 to determine the capacitance of capacitor. Yep. Just take a value, any value, easy to read, Q over V. Q over V, I take it 10 volt. 10 volt, then I read it. Okay, it's your choice. Any point you can use it. The loss in energy stored in the capacitor when the potential difference is V is reduced from 10 to 7.5 volt. Energy is half CV squared. So we are just using this formula. This is your C. This is the initial one. Initial energy, that's the final energy.